Hey everybody, Mike Hoffman here with Keysight Technologies, here to share with you the latest installment of the Keysight Oscilloscope Webcast series, where we actually taking live presentations that we did to our customers and sharing them with you here on YouTube. Today's topic is advanced triggering methods using our InfiniVision X series oscilloscopes, which is a very interesting topic for me personally. In my experience talking with our customers out in the field all around the world, most people just simply aren't comfortable with all the advanced methods of triggering built into the scope. So over the next 40 minutes or so, I'll be going through each of the advanced triggering methods in the oscilloscope, how to set them up, and what kind of signals they're designed to isolate. As we look at the agenda slide here in a moment, if there's a topic of interest you'd like to jump to, check the description below. We're going to have time tags for each of the agenda items, hot linked there, so you can skip ahead if you'd like. Without further ado, let's go ahead and take a look at the agenda. Thanks.
First off, in order to trigger on a problem, you need to be able to see the problem first, which is why we'll spend the first 5 to 10 minutes talking about how oscilloscopes can help you visualize problems on screen. Then we can spend about a half hour discussing the different triggering methods that allow you to isolate on the problems once you've seen them. And then finally, we'll wrap with some of the additional tools available in scopes before adjourning the session. Keysight scopes have advanced capabilities that can help you reveal signal anomalies as well as isolate signal anomalies. Fast waveform update rates, intensity-graded displays, mask testing, as well as search and navigation tools can help you reveal parametric signal violations on screen. And then you'll use advanced parametric triggering or alternatively zone triggering to be able to lock in on the violations you've seen. This presentation will show examples of all of these tools to help uncover various types of these signal violation conditions. First off, let's talk about fast waveform update rate. It's important because it allows you to see as much information on screen as possible. Our InfiniVision X series scopes leverage an in-house ASIC technology we've created that affords you a guaranteed rearm time of 1 microsecond. This minimizes dead time, where your oscilloscope is actually not giving you any data. Our 1 million waveforms per second is often thousands of times faster than other solutions. In this table here, we're showing the new Keysight 3000T X series side by side with the comparable scope on the market. And this test was to see the probability of each different scope capturing a 1 in a million transient over the course of 10 seconds. And you can see that the ASIC-based architecture provides maximum update rate no matter how you're using or operating the scope. Variable intensity gradation is also common on most oscilloscopes today and give you a more analog look and feel to the screen. Rare occurrences, such as the slow edge outlined here in red, show up as a little bit dimmer than the more common signal shapes. It's also helpful for visualizing modulated waveforms, as seen on the green trace here on the right. Its quick and simple visualization capability takes guesswork out of your initial testing, kind of gives you a third dimension to the signals you're looking at for the first time. Another tool we use to help visualize that we'll actually explore in a little more detail later on in the presentation is mask testing. Now, our InfiniVision X series, again with that hardware-based architecture, allows us to complete up to 280,000 mask tests per second. So if you run the numbers on that, you can actually do a pretty complete Six Sigma test in just a matter of seconds. Not only that, this entire interface is completely programmable, so it's great in automated testing environments. As a quick comparison to put this into real-life terms for you, you can see in this particular example we ran almost 2.5 million tests in a matter of 12 seconds. While in other solutions that are running more software-based mask testing, you're going to get in the range of tens of thousands in the same time frame. So why is all this important? Well, if you can visualize your information on screen faster, it gives you a faster time to test, more efficient root cause analysis because you get to spend more time solving a problem instead of trying to find it. You'll reduce failure rates in the field. And then as a kind of a kicker here, we also offer the longest calibration cycles in the industry that is afforded to us by the ASIC technology that doesn't get nearly as hot as a processor-based technology. Less heat cycles means a longer calibration cycle for the product itself. And really why this is important is because all of the advanced triggers we're going to learn today are completely useless if you aren't aware of a problem existing in the first place, because your equipment isn't showing it to you. So first I want to take a brief look at what are the 3 kind of problems that people generally run into that they need to pull out an oscilloscope for. So there's kind of three main categories of signal violations we'll be exploring today. The first is the ever-so-present glitch. Now, this is something that's coupling into your signal, perhaps an unshielded power supply or some sort of electromagnetic noise coming into the line, whatever it might be. And if this glitch is improperly timed, it's going to mess with the receiver, and you're not really sure if you're going to be reading ones or zeros on the receiver end. Additionally, we have what we've referred to as a non-monotonic edge. This is something that rises to the logic level intended, but might take longer to do so. Common reason for this might be a matching issue. And again, depending on how slow that edge is, you might be reading a 1 or a 0 incorrectly. Now, the third one, this is kind of the real nightmare, I would say, of the three, is the metastable edge. This is when you just have all kinds of noise and problems where there isn't really a way to quantify it, but you're just getting either a 1 or a 0. And again, this is probably the worst of the three. These are the hardest to characterize and find the root cause for. And it kind of encapsulates all of the problems you might encounter on your circuitry. So I want to start real quick with a poll question here, and I want each of you to, on the next slide here, tell me if you've seen one of these three kind of problems in your circuitry before, or if you've had to debug one of these three things on an oscilloscope. So go ahead and check the box for each of the three that you may or may not have ran into. Hit submit. I'll give you everybody about 20 seconds here, 15 seconds, and then we'll jump to the poll results and see where we're at. Okay, let's take a look. All right, so it looks like people are running into all kinds of issues here related to these three problems. So that's great. What that tells me is hopefully you'll walk away from this session today with some more tools in your back pocket to help you hunt these things down and get to your root cause analysis faster. So first, let's talk a little bit about, just for a few minutes, kind of how you set up a trigger and why, and then we'll jump into the advanced techniques. So first off, what is a trigger? What are we trying to accomplish? Well, what we're trying to accomplish is a stable frame of reference on a repetitive signal, which is typical on a scope. So, for example, on the left here, we're looking at a time-lapse photo of Saturn over the course of 30 years, and the only way this photo would make sense is if you're taking consecutive photos from the same frame of reference. As opposed to an unstable trigger display, which you've probably seen on a scope before, where the waveform is actually moving in time on the screen, which doesn't really give you a good frame of reference. So setting up these advanced triggers, or any trigger in general, that's the goal. Now, what happens if you don't set up a stable trigger? I'm sure everyone's seen this on their screen before. They plug in their scope, they plug into their signal for the first time, and they get a whole bunch of stuff on the screen that is unstable. This is actually what the scope looks like when you've given it a trigger condition that it cannot find. And it can actually do one of two things in this scenario. So you've given the scope a set of rules to take pictures of something in a stable way. It can either trigger on its own and just start painting information on screen, which is the default state, or you can turn on what's called normal triggering. You can actually tell the oscilloscope to do nothing at all until it finds a valid trigger that you have defined. And this is very useful for rare events where the scope might become impatient. If it doesn't see a trigger for, say, half of a second, it's going to start auto-triggering, where with normal trigger, it will go into babysit mode and literally do nothing at all. And you can imagine why that would be very frustrating to have as a default setup. If you plug into your signal, you don't have your trigger set up yet, and you see literally nothing on screen. So that's just a little behind the scenes, and you can actually toggle that. On our touchscreen interface, all you do is tap on the word auto, and it'll switch to normal mode for you if you're looking at rare events. On other oscilloscopes that are non-touch based, you'll find it pretty simply in the trigger menu. So, standard condition is an edge trigger. So what we're looking at here is a pretty complex signal with an edge trigger set up right in the middle of the screen. So every time the signal crosses the voltage threshold, paints a picture. But what if you're trying to lock in on something you see on the screen? So what we need is a mathematical way to uniquely describe a signal of interest, and that's where all these advanced triggers come into play. There's a number of different ways to uniquely describe a particular wave shape, from how fast it transitions between certain voltage thresholds to how wide a pulse might be, etc. And that's what each of these advanced triggers are trying to accomplish, to give you a unique way to describe what you're looking for to the oscilloscope. And over the course of the last 50 years of oscilloscope development, it's pretty much got to a boiling point where we have an advanced trigger for pretty much every common signal type. So what are the different types of triggers we'll look at? So we'll look at the basic ones here real quick: edge trigger, digital pattern trigger. We'll look at zone trigger, which is actually something unique to our architecture here on these Infinivision X series oscilloscopes, called Infiniscan Zone Touch Trigger. Take a look at that. We'll take a look at every single one of the advanced parametric triggers that we offer, as well as how you can dovetail zone trigger to combine with these advanced triggers, and or use zone trigger in lieu of the advanced triggers. So you do have some options here. We'll take a look at some serial bus triggers as well, but I don't want to steal the thunder on that because we actually are going to be dedicating a complete webcast to that topic, which you can find on the group registration page that you found this webcast on. So first, basic edge trigger, very simple. You define a voltage threshold. If a signal crosses that voltage threshold, it gets painted on the screen. You can choose a rising edge, a falling edge. You can choose alternating edges. So this is great for like double data rate clocking, where you want to see alternating rising, falling. Or you can see all edges, which is actually very useful for creating rudimentary eye diagrams, which is mostly used in high-speed serial, probably outside of the bandwidth of the scopes that we're looking at today, but can also be a really good way to get kind of a 10,000, 20,000 foot view of the quality of your circuit. You see if there's a lot of jitter, if there's a lot of noise, etc. Very easy to set up. It's the default trigger condition. You're going to get to it mostly by just hitting auto scale and letting the scope do most of the beginning legwork for you, and it gets you right to an edge trigger. Alternatively, we have a digital pattern trigger, which is usable on our MSO or mixed signal oscilloscope varieties. So what the pattern trigger is doing is looking at the either 8 or 16 digital inputs that you're feeding into the scope and looking for a particular logic state. Now this is not state analysis, this is timing analysis. So it's essentially looking for a particular pattern of ones and zeros at any given time, and it can lock right in. So what options do you have? Well, we have a qualifier, so you can define a very specific logic state for that bus, also a range. So you can look for a greater than, a less than, or a within or without a particular range. And you can also set a timeout. So if a particular line goes dead for some amount of time, you can use that as a trigger condition. You can either enter it using the analog input. So this is actually for the 4 analog channels on the front, so you can actually define these in tandem with the 8 or 16 digital states. You can enter the digital states of explicit ones or zeros or don't cares across all 16 lines, or 8 lines in the case of our 2000X. And then you can also define the first 8 and the last 8 in hex using the bus inputs. And you have a full hex keypad, touchscreen keypad, here on the display that you can use to simply type in what you're looking for. Now, zone trigger is something that might be new to some of you folks, so I want to take just a minute here to look at it, and then, like I said, we'll be revisiting it throughout the process. So what we just saw in this animation is our non-monotonic edge popping in and out of existence. Now, let's say we decide we want to trigger on that. But let's say we haven't picked up a scope in a couple months, right? We found that maybe the average engineer that's not a power user might use a scope a few times a month when they got to pull that out and look for a problem. And most people don't go much farther than edge trigger because it's difficult to remember all of these advanced triggers that they may or may not have learned yet. So what we decided to do is invent this. It's basically point and shoot. I'm going to go ahead and let it play, and hopefully it speaks for itself. What we've just seen is we're defining a region on the screen in voltage and time, and we're telling the oscilloscope to only paint an image if the signal passes through this zone. Now, the power of this is that it's a 2-stage trigger, so you can set up whatever trigger you want on the forefront. In this case, we were using a basic edge trigger, and then you go ahead and draw the zone on the screen. Now, there's a couple different ways we can play with this, so I'm going to show us a second example that leverages the alternate logic, which is must not intersect. For this particular example, we're looking at creating what's called an isolated 1-bit. So we took a digital pulse coming through the signal, we're triggering on rising edges, and we can actually tell the oscilloscope to ignore signals that rise or fall too close to our 1-bit. This is a common measurement that are made in high-speed serial buses, where you want to characterize a single bit in time and make sure that bit's wave shape is not influenced by ringing from previous or following bits. So it's very simple. just draw those boxes right there and say do not intersect. And now it's going to be able to, again, isolate. So we'll look at some more examples of this as we move through, and I implore you to ask any questions you might have about the technology in the Q&A. Okay, so those are kind of the basics. Let's take a look at the available advanced triggers we'll be looking at today. We'll start with pulse width trigger, what we call edge then edge, nth edge burst, setup and hold time, runt, and rise fall time. Now, the next poll question I'd like to ask is just have you used one of these advanced triggers before? Let me know if you've kind of gone down this path and how often here. I'll give us about 15 or 20 seconds here. Go ahead and just let us know, how often do you use these advanced triggers? Or maybe you never have before, and that's why you're here today. Okay, let's see where we stand here. Okay, so as we expected, there's some power users here, which is great, but it looks like most of you have never or rarely used these advanced trigger conditions. So let's start taking a look at how each of these operate and why, and we'll jump right into it. So I'm going to start just right at the top of the trigger type list and move our way down. So first I want to talk about edge then edge trigger. So what we're looking at here is a very complex signal with some RF burst and some intermediate slower bursts on multiple channels. And you can see the trigger display here is unstable. We have signals all over the place, and that's because there's a lot of rising edges on this signal that we're not interested in, but we're triggering on anyway because of how the scope is set up. So the first step you want to take is to switch your trigger type from edge to edge then edge. The way edge then edge triggers operate is it looks for an edge on what we define as channel A, and then it looks for an edge on channel B after a user-specified delay. So let's take a quick look at how all of those different parameters are set up here in the trigger, and then we'll take a look at how the signal gets acquired on screen. So first let's dive into the sources menu. Here's where we define the arming edge and then the triggering edge. Now, in this particular signal, if you see how it's set up, it looks like channel 2 is much more stable than channel 1 from a wave shape perspective. So we're going to tell the oscilloscope we're interested on arming on channel 2. And then we're going to tell the scope what we're really interested in is looking at some data later on in the waveform on channel 1. So now our triggering edge is going to be set to channel 1. So we're arming on channel 2, and then we're telling the oscilloscope to center somewhere on channel 1. Now, where do we center on channel 1 is what we define next back in the root menu. First, we can set up a user-defined delay. Now, in this particular signal, it's very useful. We have a high-speed RF burst at the beginning of our waveform on channel 1 that we're not really interested in. So we can set up a 2 microsecond delay to tell the oscilloscope to wait 2 microseconds before it starts looking for something to trigger on. And now we see we have a second option called nth edge B. So once the delay has occurred, the oscilloscope can now count out edges, rising edges on the signal to trigger on. So we can actually see that right here. So we've triggered on the rising edge of channel 2, 2 microsecond delay, and now we've triggered 2 edges later. Now, of course, we can modulate that nth edge B value there. So here's, for example, changing it to the third edge. No problem. If you have any questions on the edge then edge trigger, please leave them in the chat window. We're going to move on to the next trigger condition, which is a little more common. This is called the pulse width trigger. So what we're looking at here on the screen is actually a screenshot. Our oscilloscopes offer built-in help text that often is accompanied by diagrams and pictures for each of our advanced triggers, and actually many of our advanced measurements as well, which we'll discuss again in a later webcast for later on this year. But pretty useful. So you set up a trigger and you just press and hold on a button, and you're going to get built-in help. But what the pulse width trigger does is it's going to look at your trigger level that you've set and look for a signal that rises and falls across it twice in a row in opposite directions, and it defines that as a pulse. And you can set a time value for that pulse as well. So again, let's take a quick look at an example of why you would need a pulse width trigger, how to set it up, and then alternatively how to use zone trigger to accomplish the same task. So first, let's take a look at this glitch signal that we've encountered in the past. So it doesn't look like the slide's animating, but we'll see it here shortly. What we're looking at is actually a clock signal with a 1 in a million glitch popping in and out of existence in the middle of the screen. So what we need to do is define a pulse width trigger that locks in on things that are narrower than the pulse width of our normal clock signal. And that way we'll find all glitch violations pretty readily. So let's take a quick look at how that gets set up. So the first thing we do is we switch from edge trigger, which captures all edges, to our pulse width trigger. And you can see in the background of this image here, the scope is now auto-triggering because we haven't set up a proper trigger condition yet. So we've got to go through all the parameters listed on the bottom of the display, set everything up mathematically. So we'll switch to pulse width. We're actually okay with the source, so our signal is channel 1. We are looking for a positive pulse, but we're looking for a pulse with a certain width. Now, you couldn't see it in the animation, but the pulse that we're looking for is less than 50 nanoseconds, where the actual clock itself was closer to about 200. So we're going to go ahead and type in a qualifier value of less than 50 nanoseconds here on the on-screen keyboard by hitting 50 and then N for nano. And then we see the oscilloscope still isn't triggering. Now, this reckons back to what I mentioned at the beginning. This glitch that we're looking for is so uncommon that it's occurring, that the time between occurrences is longer than the oscilloscope will wait in auto-triggering mode. So all we do is take our fingertip, we tap on the auto key, and we're going to bring down the top menu here, and then we're going to tap auto again to switch it to normal mode, and we're done. And then we've locked right in on that glitch that we were looking for. So you can see it's fairly simple. Again, we're just looking for a mathematical way to uniquely describe this signal. Now, of course, there's a way we could do this with zone trigger as well. So it looks like now it's animating. We can see that glitch popping in and out. So what could we do to describe this signal visually instead of mathematically? Well, like we saw previously, we can actually draw a zone on the clock and say it must not intersect. And now the signal is going to, the oscilloscope's going to ignore all good signals that pass through that zone and lock right in on our glitch. And that's how we were able to do it in this case. Now, the beauty of zone trigger is, again, it is so flexible that your mileage may vary, right, depending on what signal you're looking for. But we'll look at a number of different options today, and it should be fairly easy for you to conceptualize in your head how you could use or could have used zone trigger to lock in on trouble signals you've encountered in the past. Okay, so the next one we're going to look at here is a rise fall time trigger. So if you remember back from your EE 101 days, we defined the rise time and fall time of a signal by how long it takes to rise from a low level to a high level that we define. Most low-speed signals, we're defining how long it takes to rise from the 90% voltage, or from the 10% voltage to the 90% voltage, or vice versa, how long it takes to fall from 90 to 10. It could be 20, 80. It could be whatever you want, actually. And what we'll see here in the trigger setup is you define these levels yourself. So let's take a look at what a signal looks like with a basic edge trigger, how we lock in on it using the rise fall time trigger, and then how we can additionally do it with zone trigger. So first, this is run out of an auto scale. We're looking at a digital signal. Just hit auto scale right in the front panel there, and this is where we sit. So the first thing we probably want to do is zoom our time base in, take a look at the edges a little bit closer. And then I'm also going to switch the edge trigger type to either edge. So we're seeing rising and falling edges on the screen at the same time. And we can see pretty readily there's some violating edges that are a bit slower than the edges that we actually want. Now, I'll save you all the math here, but in the background, I've turned on the cursors. I've measured the rise and fall times that we're interested in. The good rise time is somewhere in the range of about 50 nanoseconds, and the bad rise time is somewhere in the range of about 120 nanoseconds. So it should be fairly easy for us to define this trigger condition with that large of a delta between the rising edges that are good and rising edges that are bad. And you can see I've done that actually here with an automated measurement as well. So with our statistical analysis tool, which is pretty neat, we can go ahead and see those maximums and minimums pretty readily there on the screen. So let's go ahead and start locking in our trigger. So first we're going to switch from edge trigger to rise fall time trigger. And we're going to look down here at our trigger input conditions. So first off, source. Our source is channel 1. We're still good. We have a toggle switch there, whether you want to see rising edges or falling edges, so we'll keep it on rising edges for now. Next, we need to define our high levels and our low levels, and we do that with the level select key. So with level select to high, we can use our trigger knob to adjust, and you can see with the red arrow there, our high level trigger to roughly 90%. And then we toggle that level select to low, use our trigger knob to bring that down to about 10%. And then we need to define our threshold. In this case, we saw about the 50 and the 120. So we're going to go ahead and enter in a time of 100 nanoseconds. And now you can see the scope is uniquely locked in on any signal that takes longer than 100 nanoseconds to rise from the low to the high thresholds we've set. And if we're so inclined, we can hit that toggle switch it to falling edge triggers, and we can see it does just that, locks in on our falling edges as well. Now we can move forward with character. So how can we do this with our visual triggering system, InfiniScan Zone Trigger? Okay, no problem. We can see the signals there on screen. All we need to do is draw our zone and give the scope the proper logic. So in this case, I'm going to go ahead and draw a zone on the falling edge such that the zone does not touch the good falling edge until it intersect, and you can see it's locked in there, no problem. Okay, so for our next advanced trigger, we're going to look at the nth edge burst trigger. So what this one does is it lets you trigger on the nth edge of a burst that occurs after a specified idle time. So the signal coming through, the scope is going to be looking for a state of idle for a user-specified amount, and then it's going to count a number of edges. So it's similar to the edge then edge, but it's for use on one channel. So why would you need this? Well, let's take a look at a particular signal here. In this one, we're looking at a digital burst. Each burst is about 45 microseconds long with about a 10 microsecond gap in between them. So here we're just triggering on rising edges, and you can see our screen is unstable because there are a ton of rising edges within our digital burst. So in order to lock in on this uniquely, we need to set up a trigger that describes the signal uniquely. Now, to quickly prove the point, I'm adjusting you can see a value there on the bottom in green called hold off. This trigger hold off mode allows you to tell the scope to wait a specified amount of time between triggers. This is great for bursty signals as well. So you can see I'm going to go ahead and set the trigger hold off to 45 microseconds because I know it, and I'm going to hit single shot, and we can see pretty simply there that there's a gap of about 10 microseconds, about a half a division wide, between about 2.5 divisions of signal, or about 45 microseconds wide. So what if we want to trigger on a specific edge within that burst? So let's go ahead and set that up. First, change your trigger type from edge to nth edge burst. We look at our parameters here. Again, not too many options, only 4, so it should be pretty simple. We want our source to be channel 1. For this example, we will say we are interested in rising edges. We do want to set our idle time, so you can hear here I'm setting it to 5 microseconds, which is longer than any specific pulse width within the digital train. So if say you have a bit period of 5 microseconds, this wouldn't work. So you want to set a value that's long and that's shorter than the gap between bursts, but longer than any specific pulse within your burst. So 5 microseconds is the value we're using. And then let's just pick the third edge. You can pick any edge you'd like. And you can see now, the signal is actually stable and locked in on what appears to be the third edge, and we can zoom in and check. And we can see here, yep, so we were idle for at least 5 microseconds, which is longer than any of those wide pulses you see in there. And then the scope is counted out 1, 2, 3 rising edges based on your trigger level, and it's centered right in on that. How can we add zone trigger to this? Well, actually, in this specific case here, I'm running the scope again with that trigger condition I just set up. And in fact, our digital train has enough variability within it that there's a number of different waveforms that qualify for this trigger. So it is still somewhat unstable. We're still seeing a number of signals on screen. So what we can do actually is use our zone trigger in tandem with the advanced trigger we just set up to further isolate and drill down on a signal we want. So we're going to look at here is just a zone trigger that has been set up to isolate one specific waveform on screen based on the shapes that you see on the screen. So again, just want to bring home the point, zone trigger works best with edge trigger because you can use it in lieu of a lot of these advanced triggers, but you can use it in tandem with them as well. Next, we're going to take a look at runt trigger. So the way we are conceptually defining a runt is that we have a low level and a high level. And the scope is looking for any signal that passes through the same level in opposite directions without passing through the other one. So you can see for the positive runt pulse, the signal crosses the low and then crosses the low again before hitting the high. That's a runt. The negative runt, it crosses the high and then crosses the high again without crossing the low. That's a runt. Now, of course, this is a problem, so we obviously have a trigger to allow you to drill in and find those problems. So again, we're going to start with an auto scale. We pull up our scope, plug in the signal. Auto scale is always a good first step. And we got an edge trigger set up. So the edge trigger is capturing all the runts as well as all the good edges that we like. And we can see it here on screen and go, okay, we got a problem, and it's a runt. So, of course, what we want to do is move forward with setting up a runt trigger to lock in on them. So, of course, as always, first step, switch our condition to runt. We can see the signal in the background is now not triggering correctly because we don't have our runt trigger set up yet. We're going to look down at our options. So we're okay with the source being channel 1. That's great. Our next one is a toggle switch. We can look for positive runts, negative runts, or all runts. So we're going to leave it on just positive runts for now, and we'll play around with that in a second. And then we got to, just like we did on previous triggers, we got to set our level selects for high and low. So for our high level, we're going to move that trigger level to just, it doesn't really need to be 90% or 80%. It's just whatever value is in between the maximum value of the runts and the maximum values of the good signal. So you can kind of see it in the background there, the dim lines of the runts going across. As long as it's between those two, you're in good shape. And then same thing with the low-level trigger. And as soon as you set the low-level trigger, boom, we've locked in on our positive runts. Additionally, we can set up a qualifier, so you might have runts at different lengths. In fact, in this signal here, you're seeing two signals at the same time on screen. So let's say I'm interested in one or the other. I'm actually going to zoom the time base out one click, and we can see it more readily. We have two positive runts here on the screen triggering simultaneously. One's longer than the other. So if we look, one's about 1 bit period, and one's about 3 bit periods. And we can see from our scaling on the top, a bit period's about 100 nanoseconds. So let's set up our qualifier around the, say, 200 nanosecond threshold. And then we can lock in on the longer one or the shorter one selectively. So first, if we look for longer than 200 nanoseconds, okay, great. We've locked in on that long run. And then we can just switch the qualifier to less than, and now we've locked in on the short run. Now, hopefully your signals aren't any worse shape than this demonstration signal, but you might have multiple runs, more than 2, and so you can kind of play with this value a little bit more to lock in on exactly what you need to see. Now, what if we switch the logic? Let's look at the negative runts as well. No problem. Okay, now we've locked in on 2 unique negative runts, and again, we can play with that qualifier switch to lock in on the longer runt, which in this case is 4-bit periods, or the shorter runt, which in this case is 2-bit periods. So how could we do this with a zone trigger? Well, again, this is where it gets kind of fun because you got to get a little creative, right? So you could do one thing. You could draw a really, really small box on one of the runts and click must intersect, but here's a little bit of an easier way to do it. In my opinion, just set up not intersect zones where the good signals are touching. So press do not intersect on the signals that rise to the full value, and then you can actually include a second zone on the screen like we saw before to switch between the longer runt or the shorter runt, depending on what you're interested in seeing. If you have any questions about runt triggering or what we just saw, again, go ahead and plug those into the Q&A, and we're going to move forward to the next trigger. So for all of you digital designers out there, this should probably look pretty familiar to you. What we're looking at is a setup and hold time trigger. It's often used for violations, but you can also use it to lock in on proper setup and holds as well. So it's just defined as a general setup and hold time trigger, and it works by looking across 2 different channels. You define your data channel and your clock channel, and you can set up variable amounts of setup time or hold time to lock in on particular delta times between those 2. So let's take a quick look at an example of why you'd need something like this and how to set it up. So here, again, we're fresh off on an auto scale. I've also used the labeling feature inside the oscilloscope to explicitly define channel 1 as clock and channel 2 as data. And you can see that listed there on the left side of the screen. Cool thing about that is now anywhere in the context menus you used to see 1, you'll now see clock. So if you're working with a lot of signals, that can be really useful for you when you're maneuvering around the scope. You don't have to remember which channels are what. So we're triggering on rising edges of the clock, and we're simultaneously seeing the data down below. And we can see for the most part it's doing a pretty good job of latching the data before it gets to the top of the clock, assuming the falling edge of the clock is where we're clocking data. But we also do see some violations there. We do see very dimly down below some rising or falling edges on the data they're creeping a little bit too close to the clock edge that we're interested in. So let's say, for example, maybe the setup time for the good signal is something like 37 or 40 nanoseconds. Okay, that's fine. Then the bad one's getting closer to the 20 or 15 range, or maybe that's below spec. So we want to lock in on that, and then maybe dial out a bit and see what is it in relation to, how often is that happening, plug some other channels in, see if there's any correlation there, etc. But again, if you see a problem, you got a trigger on it to go to the next step. So how do we do that? So I've used the cursors here, again, just to kind of conceptualize. We're looking at 38 nanoseconds for our good edge, so anything less than that would be a violation in our eyes. So, as always, our first step is to go ahead and switch our trigger condition from edge to setup and hold. And again, you see in the background the scope has stopped triggering correctly. It's because we need to set up our trigger still. So let's take a look at our parameters. We have clock, already set up on channel 1, which is clock, so great, saved us a step. We are interested in rising edges. Our data is already defined as the data channel. Okay, great. Now we set up our setup and hold thresholds that we're interested in locking in on. So as we defined previously, we saw our good was about 30 or 35, our bad was 17 or 15, so 20 is a good threshold there, and you can see we've immediately locked in on all violating setup and hold time conditions for this particular signal. Again, now at this point, you might want to hit single shot, go back and take a look at what happened before, right? Is there some correlation there? Plug in some other channels. You might want to turn on our segmented memory tool, which we're going to look at shortly. See how often is this occurring? Is there a pattern here, etc. Now, again, I'll spare us the animation. Hopefully you're all kind of understanding the gist here. Let's take a look at how we do that with zone. Again, very simple. But in this case, we do need to switch the source of the zone. So we're using a zone on channel 2 now instead of channel 1 that we've used before. And we just draw a zone such that the rising and falling bad edges go through our zone, while the rising and falling good edges pass around the zone, which allow us to lock in on those wave shapes uniquely. So you can kind of see there's a difference. So zone trigger generally 1 or 2 steps. These advanced triggers generally require a little more legwork. Okay, so we're 40 past the hour. Looks like we're right on time. Perfect. So I want to spend just a few minutes here looking at serial bus triggers. So before we do that, I want to quickly ask, how do you currently debug serial buses? Are you using automatic decodes on a scope already? Maybe this isn't new to you. Are you hitting single shot and manually counting ones and zeros on a piece of paper? Are you using a protocol or a logic analyzer? Are you using something else? Or is this lost on you? And let me know. Here we go. We'll give you about 15 seconds to plug something in there. All right, let's see here. Okay, well, very cool. So it looks like we have a majority here, probably by a single vote, using automatic decode on the scope already. That's awesome. So hopefully you'll attend our serial bus triggering webcast coming up here shortly and maybe learn something you didn't know about what's available on today's scopes. But if you're still using manual bit counting on a scope, this would hopefully be an exciting couple slides for you, and you can see where the technology is nowadays. And if you're using a protocol or logic analyzer, you might see these as a great kind of a secondary tool. So while the protocol and logic analyzers give you great information, state analysis, etc., scopes do allow you to see the physical layer. So you might see a value there as well. So let's take a look at just a couple different triggers available. We'll do a quick overview of everything we've got, and we've also got a great deal around this. So let's take a look. Obviously, probably the most simple serial bus we probably all agree is SPI. So here's an example of our SPI triggering. So cool things that we offer that are pretty unique. So we give you a split screen view. So you get kind of a quasi protocol logic analyzer timing view on the top, and then you can see your actual waveforms down below. We also offer time-aligned decode there in the bottom of the screen. And for SPI, of course, it's pretty simple. You want to trigger on MOSI or MISO, how many bits, and then you can enter in a specific base for how you want to type in the data you're interested in. Then we also offer a variety of more complex triggering conditions. Now, I2C by no means I would say is a complex serial bus, but you can see we've fleshed out all of our serial bus triggers to really allow you to lock in on anything you're looking for, especially if you're able to see it flashing in and out on the screen with the fast waveform update rate, then you're going to want to take the next step and lock in on it. So For I2C, you can see quite a variety of triggering options there, and then some other fields that will light up depending on what you're trying to trigger on. So defining an address and defining some of the data that goes into the bus. Outside of that, we also offered a huge variety of other trigger conditions as well. So you might see something that pops out on the screen here. Again, I don't want to steal Johnny Sunder. He'll be doing the serial bus webcast here shortly. But you can see we have three sectors. We have our automotive decodes. It also tie into manufacturing pretty well with CAN as well on the left. Our general purpose stuff is on the right. We've got some military applications on the top. So the beauty of this, too, is with our app bundle that we offer, if you're interested in this, go ahead and tap into MicroLease or your preferred distributor. But you're going to get every single of these serial bus options as well as every single other option in the scope for one low price. So which is pretty exciting, and it means no more bit counting, no more human errors, and you're going to get faster time to test. So now that we've talked about the triggering, I also want to kind of dive into a few of the advanced applications we mentioned at the beginning. First, I want to talk about something I mentioned. So I mentioned search and navigation, and you might have seen the footnote I'd added. So there's kind of two trains of thought here. There's search and navigation, and then there's a tool we have called segmented memory that help you capture multiple events on screen. This allows you to analyze maybe delta time between errors, if there's any repetition to this error, etc. So traditionally, if you wanted to capture multiple errors that you're triggering on, you'd zoom your time base out far or maximize your memory to the deepest amount of memory. And then you're going to go ahead and do a single shot. And then you're going to use the search and navigation tool to actually go through and look for the signal violations we've been setting up as triggers. So take a big deep shot, capture a whole bunch of stuff, and then instead of setting up a trigger, you'd set up a search routine using the exact same steps. And then hopefully you caught one. And hopefully you caught two. Otherwise you're just catching one, and it depends on how infrequent the event is, etc. So while we do offer the traditional method, we decided to take a different spin to solve that kind of problem. If you're looking for multiple events, what we're going to say is if you can view the problem on the screen with a fast update rate and trigger on it using advanced triggers, we can give you up to 1,000 consecutive events based on that trigger condition. And now you can go back and look at basically a replay of the last 1,000 times a particular trigger occurred. So pretty cool. So let's take a quick look at what that means for you. So here's the traditional method. Again, zoom out, use as much memory as possible, single shot, search. Problem with this is memory depth is fixed. No matter what oscilloscope you buy, it's going to have some sort of maximum amount of memory. And if you want to capture more time, you're going to have to sacrifice the only other variable in this equation, which is sample rate. So memory depth is fixed. If you want more time, you sacrifice sample rate. If you want more sample rate, you sacrifice time. And, of course, the problem here is the lower your sample rate is, the lower your bandwidth is. And if you're undersampling too much, then your oscilloscope's going to have trouble capturing these events you're trying to find because they're being aliased or undersampled. The reason for this is the scope is spending a lot of memory digitizing things you don't care about. So in this particular picture, this pulse here represents our trigger condition or event of interest. There's a lot of dead time in between. You can see a vast majority of the oscilloscope's memory is digitizing all the stuff you don't care about. Here's an example, actually. We're using that 1 in a million glitch. Now, this actually took me about 50 or 60 single shots to actually capture a single event. And that's because if I zoom my time base out too much, the glitch is going to be aliased. But the glitch is so few and far between, I can't zoom out far enough to capture two on screen at once. So in this capture, we've actually caught one. And that took me a while, but I was able to get one. Now, if we do the segmented memory route, which is this here, all we do is define our trigger condition, zoom the screen in such that that pulse is taking up most of the screen, and then we enable segmented memory, and we can capture, again, up to 1,000 of these. And what's happening is it's kind of like a smart DVR, where it's ignoring all the stuff in between captures for you. In this particular case here, we did a segmented memory capture on that glitch, and I actually captured 1,000 of these glitches over the course of 280 seconds at full sample rate. Now, I could do the math and tell you how much traditional deep memory you would need to do this with a single shot, but it's actually an order of magnitude larger than the deepest memory you can buy on any oscilloscope on the planet today, and that's if you have $500,000 burning a hole in your pocket. So what we're looking at right here is a capability that you simply can't emulate without this segmented memory tool. So here's another example of segmented memory as well, and something that's a little more realistic and a little more common. So we can actually take that Runt pulse example we used before. I'm actually going to set up a trigger to trigger on all Runt types, and then segmented memory capture to capture a number of consecutive Runts. So you can see here I've gone ahead into the Runt trigger. I'm telling it to look for all trigger types, or all Runt types. So we can see all 4 of our Runts, the 2 positive and the 2 negative, all overlaid. And then I can set up a segmented memory pretty simply. So I go into the Start menu in the corner, I hit Setup, and then I hit Acquire. And then I want to acquire segments, so I'll click the Segmented key. I'm going to enter the number of segments I'm interested in, so I've just typed in 100. And then I'm going to press the On key, basically, down there on the left, the Segmented key. And now I've captured 100 consecutive Runts of all different types. And you can see over on the right we have an event lister, where every single one of these segments is time tagged down to the accuracy of the sample period. So in this case, I'm sampling at 5 gigasamples a second, so my timing accuracy is down to the actual sample itself. So very accurate. Now you can export this information to Excel or whatever you need to do to take it off the scope to do more deep dive analysis. Another great visualization tool was mask testing. So here we're looking at the error rate of a specific glitch on screen. We can see we've captured over 10 million tests in the course of a minute with a particular failure rate. And there's actually a number of options that we can set up on this mask test. So it's very easy to find. You hit Analyze, and then you turn on the mask test feature in the feature list. And for example, here we're going to look at the error rate of the bad edge. So I can go ahead and turn on what's called the auto mask. So I click the auto mask key and create mask. And what it's going to do is automatically create a mask around the most common signal on screen, and then again start counting failures and errors for me. So great top-level view, great for manufacturing or QA kind of situations. And there's a number of different options you can set within this mask test. So you can tell it to stop after a certain number of tests or a certain signal level getting reached. You can have it stop if there's a violation, so you can come back and look at it. You can even, using bench view, set up the oscilloscope to send you a text or an email or a notification on your phone when these kind of events occur. So a lot of power here, great for long-term testing. And the last thing I'll leave us with before we wrap up is what happens if you're triggering in a noisy environment. Now, you're probably looking at this going, yeah, I've seen this before, right? So if you're in a lab environment, unless you're in an anechoic chamber, you're getting all kinds of noise from the environment, and you're going to see this. And basically what we're seeing is the rising edges of the noise that are riding on top of the falling edge of the signal are large enough to trigger the oscilloscope. So when we're telling it to trigger only on rising edges of the signal, it's actually capturing rising edges on the falling edge as well, and we can prove that by zooming in. So I did a single shot on a falling edge, and we can see there's actually a 160 or so millivolt rising edge riding on top of the falling edge. So what can we do to enhance the use of the scope in these kind of environments? Well, there's actually 2 tools available to you that we'll look at here shortly. First off, we call high-frequency reject. Now, within the actual path of the oscilloscope, the memory gets scoped in from the analog to digital converter. It gets sent to the acquisition memory to be displayed on the screen. The information also gets fed into our trigger circuitry in parallel that allows the scope to define the trigger point within the memory. And what we're doing here is putting a filter on the triggering circuit. So the signal you're seeing on the screen is not filtered, but the trigger circuitry is being filtered with a 50K low-pass filter. So this is great. Classic example is you're looking at a power line, 60 hertz, and you're getting all kinds of noise from the environment, such as radio stations or cell phones that you know are higher than 50K. So you're seeing the real signal, but you're getting a stable trigger. Another tool you'll find in the trigger mode menu is noise reject that you'll see down there. So if we turn on noise reject, what this is actually doing is adding more hysteresis to the trigger circuitry. So what it's doing is that now that 164 millivolt rise is no longer valid. It needs to rise farther than that in order to qualify as an actual trigger. The exact value is somewhere in the hundreds of millivolts. And the only downside to this, though, is if you're looking at a real small signal, say anything less than about half of a volt, this is no longer going to work because the signal itself isn't large enough to get past the hysteresis bands in the trigger circuitry. So something to keep in mind, works great for larger signals and gets rid of the problem we were just seeing.
All right, everybody, if you've made it this far, thank you so much for your attention and watching today. We'd love to hear your opinions and feedback in the comments below. And to stay in tune with all the latest live webcasts that we'll be sharing on our channel in the future, make sure to like and subscribe. Thanks so much for watching.